We have seen this integral a couple times in the course already. One of the earliest methods I taught you involved setting up an auxiliary integral I alpha beta and differentiating with respect to alpha to bring down the x, to cancel this x down here, and then use Euler's trick to evaluate the integral and then integrate back to find the value, impose some boundary conditions. So that was a pretty nifty and nice method to do this integral. Later on, when we studied Fourier integral transforms, we found that one way to find the value of this integral is to find the Fourier transform, integral transform of a bump function, and then that naturally leads to evaluation of an integral like this. So there are many ways to do this integral, and this is to be taken as an additional technique. We're going to use complex analysis. So the first step is to make this into a complex integral. Now, you may have thought, why not make it sine z over z dz? The only problem with that is it's not easy to talk about what happens when z equals 0, because then you have a singularity there. So you want to keep the function simple enough that it only has a simple pole at the origin, and that's the motivation for making it e to the iz instead of sine z. And then at the end, when we are finished with this process of doing the contour integral, we'll be looking at the real line. The real line goes from minus infinity to plus infinity, like here, not the complex contour. And so we'll have to make an argument about what happens to the contour as it goes out to infinity, because as the integral goes to infinity on the real axis, the contour will be also taken to infinity in the imaginary axis. So we have to make those arguments. Lastly, we have to take the imaginary part of whatever we get in the negative infinity to positive infinity line real axis, because then that will give me, the imaginary part will give me sine x. So these are all the things we have to do. So first let's decide on the contour for this problem. Now, because I already mentioned it's got a simple pole at the origin, we have to avoid the origin like the plague. So that's what we'll do. We'll take the contour, we'll shape it so that there's a speed bump at the origin. This epsilon speed bump will keep us clear from the simple pole at the origin. When I talk about the pole structure, I'm thinking about this entire thing as a function f of z, and that function has a simple pole at z equals 0. Now, the contour itself is a semicircular half annulus, so it's going to be like that, and the contour is C, and the interior of the contour is whatever is inside it. Now observe that the interior of the contour is free of any disturbances. It doesn't have a pole or anything, so the Cauchy's evaluation of this closed circuit integral is going to be 0. So that's one thing we notice. I'm going to call the contour on this side C, and on contour on this side C prime. C prime is a clockwise contour that goes from minus epsilon to epsilon, and C is a counterclockwise contour. So I'll also put these values, radius r of the big contour, and the radius of the little contour is, of course, epsilon. So that's our contour. Now what we're going to do is parameterize the complex number. Complex numbers are parameterized using Euler's formula. So z equals epsilon e to the I theta on the curve C prime. These contour integrals have to be done on the curve. So you have to make a way of writing the complex number on the curve. So dz in this case is going to be I times epsilon e to the I theta d theta. But epsilon e to the I theta is just z again. So I can write this as dz by z equals I d theta. And that's really nice because I've gotten rid of that z. So let me just consider now that what happens to this speed bump integral. It's e to the iz over z dz, and that just becomes integral c prime e to the iz times I d theta because of this. And as epsilon goes to 0, you observe that z goes to 0. because z and epsilon are related like that. Epsilon is the modulus of the complex number. So as z goes to 0, certainly the only way for that to happen is for epsilon to go to 0. I mean, that means if z is 0, though, e to the I z is just 1. So this just gives me the integral from pi to 0, remembering how it goes from pi clockwise to 0. I just get I d theta, and that's equal to negative I pi. So I've already evaluated one small part of the integral. What about the big one? The integral from so the total integral, let's just do the total integral over the entire curve C. That C stands for this, C prime, that, so that's the entire contour C. E to the I z over z dz equals C prime e to the I z over z dz plus the integral in the upper half plane, which refers to just this part, UHP e to the I z dz over z. And now we have to deal with what happens here. Unfortunately, we have sort of failed in our mission, because our mission was to go from minus infinity to plus infinity, but here we have an interruption. So we have to use a limiting process, and this is the famous Cauchy principal value of an integral, or CPV. It's a very useful thing in engineering and other applications. So it is the integral from minus r to epsilon, and then you pay respects to the epsilon speed bump by hopping epsilon to r of e to the I z over z dz. So this has got the name of the CPV, Cauchy principal value. The word principal means it's like the only part of the integral that matters. So you should think of it like that. Okay, now there's a similar argument to this upper bound contour that its contribution goes to 0. So we'll run through that next. The star of the proceedings will be again the Cauchy-Schwarz inequality. So let's do the upper half plane argument. So now we're going to parameterize the contour on the upper half plane by another complex number parameterization, z e to the I theta. That's appropriate since the radius is r. So dz is going to be r e to the I theta, d theta, and so on. So what I'll do is I'll estimate the absolute value, or the modulus, the size of this as a complex number. This integral, all said and done, at the end of the day will be a complex number, and so it has to have a modulus. Now by the Cauchy-Schwarz inequality, that's less than or equal to the integral from 0 to pi, that's how I'm going, the absolute value of whatever is inside. Now here I'm going to write the parameterization, so that's IR cosine theta plus I sine theta by expanding e to the I theta, that's what I get. And then dz by z is just id theta. The r does not matter, whether it's r or epsilon, that id theta is still there, but the absolute value or the modulus of id theta is just d theta. So I'll just write that. So that's what you get from the Cauchy-Schwarz inequality, and by putting in the parameterization. The Cauchy-Schwarz inequality is extremely useful to get estimates. Now this is equal to 0 to pi by the property of exponentials. It just separates out e to the IR cosine theta times, now I times I is minus 1, so that gives me e to the minus r sine theta d theta. I really don't need the modulus around d theta, but I'm just putting it by habit. So this thing here, that's got a magnitude 1, because that's just e to the I something. So I'll not write that anymore. So this just gives me integral 0 to pi e to the minus r sine theta. I don't really need these modulus signs anymore. And that is always, the largest value of sine theta is going to be 1. So that's always going to be less than or equal to 0 to pi e to the minus r d theta. And that can be evaluated. That integral is precisely equal to pi e to the minus r. And that goes to 0 as r goes to infinity. So we have shown that the upper half plane contribution just vanishes. That's par for the course in these types of problems. The upper half plane contribution will always vanish thanks to an estimate based on the Cauchy-Schwarz inequality. And it's always a good exercise to show this, just to keep your inequalities in practice. And I would urge you to do this, even though we already know beforehand the answer is going to be 0. Now, I've already told you beforehand that the value of the integral in the interior of C, because the interior of C is free of any poles, the total integral is going to be 0. So the total integral C e to the iz over z dz equals 0. But that integral is also equal to a bunch of these things. So this part we evaluated to be minus I pi. The upper half plane contribution is 0. And the Cauchy principal value, CPV, of e to the iz over z dz is all we're left with. So this tells us basically the Cauchy principal value is equal to I pi. Now, what I'm going to do is take the real and imaginary parts. So the imaginary part of the Cauchy principal value of e to the iz over z dz, well, that's just going to be equal to pi. And that is the integral from minus infinity to infinity sine x over x dx. Because along the real axis, z equals x plus iy with y equal to 0. So this is just going to give me, let me just show you why that is, e to the ix, and e to the ix is equal to cosine x plus I sine x. So the imaginary part is indeed sine x. All right, now the real part, as a added bonus, we get the further result that the real part of the Cauchy principal value of e to the iz over z dz is equal to 0, and that's negative infinity to infinity cosine x over x dx. Well, not that this is something we could not have guessed, because cosine is indeed a even function and x is an odd function, so the product of an even and an odd function is an odd function, and you're integrating between symmetric limits. So that answer has to be 0 is a simple check of common sense in this case. So yet again, we have evaluated the Fresnel integral correctly.